In the previous two videos, we looked at drawing Lewis structures for elements and drawing Lewis structures for ions. Let's put those together in the knowledge that we just learned from those two videos and figure out how to draw Lewis structures for ionic compounds. So first off, let's look at something simple like sodium chloride. Now, the very first step is looking at the compound, deciding, is it ionic or is it covalent? Because if you do not do that step, you might very well miss this. If this is covalent, you draw the Lewis structure differently than if it's ionic. And so the first step, just stop and think, is that a metal and a non-metal? Yeah. What's the electronegativity difference? Look that up on your periodic table. For this one, my electronegativity difference is 2.1. So if you have an electronegativity difference greater than 2, you're typically going to have an ionic compound. If it's less than 2, you're going to be looking at a covalent compound. So keep that in mind. If it is ionic, draw it like you're going to see in this video. If it's covalent, you need to draw it like you're going to see in a future video or videos. Okay? So how do we do it? First, break this apart into its charges. So uncross those charges. This becomes sodium positive, chlorine negative. So then when we draw the Lewis structure, it's just a matter of drawing how many sodiums do I have, how many chlorines do I have. What do I mean by that? So if I were to draw the Lewis structure for sodium, you know it looks like this. And the same for if I draw chlorine, I would draw it like this, but with all 8 electrons shown. This should be how you do it, where the cation has no electrons around its central atom, and then the anion has all 8 electrons drawn. It always works out this way. Why? Everything's trying to get a happy, satisfied octet. And so if you drew 7 on here, something's wrong. If you drew 7 or 8 on here, you really screwed up, okay? But it should have 0, not 1, not 2. And so you draw the element in the middle, nothing around it, positive charge. Draw 8 electrons, negative charge. But the only difference is when you're writing the two compounds, in front of each bracket, you list how many of those atoms there are. So for sodium, there's only 1. So I could put a 1, but you don't put 1s. You put 2s, 3s, etc. So if it's a 1, you just leave it empty. And then 1 for chlorine. Okay? So in the end, this is the final Lewis structure for sodium chloride. But once again, I had to stop, think through, is it ionic or is it covalent? You're going to get really good at drawing covalent Lewis structures, and we're going to focus so much on them because it's a little bit trickier than this. You're going to forget this exists. Meaning, you're going to go to sodium chloride and you're going to be like, oh, Na bound to Cl, a bunch of dots, and I'm going to look at you like you've done lost your mind, because you have. It is not covalent, okay? It is ionic, so you draw it like an ionic Lewis structure. Let's do calcium oxide. And so when you break this apart, you may have thought calcium 1 plus, oxygen -1, but remember, they're both 2s. So that means that when they cross, they reduce to the lowest common form, which is the 1-to-1. So that means that this compound is Ca2 plus and oxygen O2 minus. And so when we draw our Lewis structures, you're going to do that same way with calcium, no electrons around it, 2 plus on the outside, oxygen with 8 electrons around the oxygen symbol, and a 2 negative on the outside, and you're finished. Let's check the electronegativity difference for calcium oxide. Calcium oxide has an electronegativity difference of 2.5, so it's definitely ionic. But let's do one now that isn't just 1-to-1, because these are a little bit more simple. Let's do, how about magnesium fluoride? And you do want to practice your naming to formula, formula to naming. Remember all those delightful things from earlier in the semester? And so magnesium fluoride, magnesium's 2 plus, fluorine's -1, and so you should come up with MgF2. So magnesium, break it apart, write the charges, and fluorine. Same thing that we did previously, write your cation first with brackets and no electrons. Write your anion with 8 electrons, brackets, and the charge on the outside. But now there's one extra step. There are 2 fluorines. So you put the 2 in front of its symbol. Magnesium is just a 1, so you can leave it alone. And so using this type of structure, we're able to see magnesium fluoride's Lewis structure is what you see here. Let's double check. What's my electronegativity difference here? This one is going to be 2.9. Now, Are these delta electronegativity differences, are those the only way we can look and say whether or not this is Lewis or not? I mean, if it's ionic or covalent? No. Let's look at it a little bit closer. So here's your periodic table, and here's the chart that was telling us about how bonds are classified based on electronegativity differences. Magnesium bromide has an electronegativity difference of 1.6, technically classifying it as a polar covalent bond, but it's definitely a metal and a non-metal. You can see they're on opposite sides of the periodic table. So this is going to act ionically. Whereas if you have something like CH4, which is going to have an electronegativity difference of 0.3, this chart works out really well because that's going to be a very non-polar bond. It is going to have a little bit of polarity differences, but not much. And so it's definitely covalent. And so when we're looking at classifying things based on electronegativity differences, we need to use our brains, but also think through the fact that even though magnesium bromide is ionic, it does have not as uneven of an electron distribution as some of its other ionic bond counterparts.